All right, here we go. I mounted onto a tripod. I actually left that on.
Then use some duct tape.
Right, I'm not putting duct tape.
That's scary.
All right.
Break your legs.
Okay, here we go.
Oh my hand.
If you would, please pull out your homework from last night.
Oh, I didn't do it. I don't have to do it ever.
Angela, I thought yesterday was quiet. Now I know why. All right.
Okay. Wait till the end of class.
Okay. Here we go. Sorry about that, Nicole. 2.0 is being difficult. Here we go. So, really quick, I'm going to come around and check your work. What I'd like you to do is there are 4 different representations that we've talked about recently in terms of ways to see functions, sequences, and series, and how we tie them all together. The how we tie them all together is kind of what we're talking about today. There was questions on the homework last night. We will go over those. However, I'll give you a hint. It was an arithmetic sequence. It's an arithmetic sequence. And if you got too bogged down in trying to recreate what we did with the last example yesterday, yes, it would have been hard.
Do we have one more?
Good question, yes. Anyone not get a handout? You too. Okay. So,
Another one.
we need another one? Alright. Okay, no worries. I just want to
I
make
didn't
sure.
really have time for
No, that's fine. I just wanted to make sure I wasn't like neglecting your time. Okay.
Take my homework.
Okay. If you could, on your own. Guys. If you could, on your own, please. Aiden. I don't have any patience for you today, man. Okay? Okay. If you could, on your own, please, please work on trying to find out. Basically, you're doing a compare contrast. What's similar, what's differences between these representations? I'll give you a hint. Think about domains, ranges, stuff like that. It'll help.
Are we working on this?
You're close.
I like writing too.
Okay.
Like that? Are you scrolling? Yeah, like that.
Yeah. Cool. Okay. Okay.
Barry, stop being weird.
Okay, by talking, I assume you're done?
No.
Then, I need you guys. Okay.
Those are table functions, one, two, and three.
All you have to do is make an equation, define an odd number, and then solve the equation.
For this one, it ends with 1.
You have to say that it ends with an odd number. I put it, you can only get it by adding an even and an odd. You can get it by adding an even or an odd and odd. Isn't that odd? Oh, hilarious.
Oh, you were in here after.
I have horrible jokes.
Talking after class. Means talking after class. You got 10 more.
It's horrible. I can't sing to save my life. Be ready for this.
Okay. Aiden, sit down. Carlos, find a seat. Barry, sit down. Okay. All right. Alrighty. So before we get to the warm-up, a couple of questions about the homework. Just some things that I noticed that I want to clear up because I think we have some misconceptions. One, when you're looking at that pattern, we have n and we've got the sequence as a function of n. Okay? When we plug in 1, 2, 3, 4, 5, dot, 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 we get 1, 3, 5, 7, 9, dot, dot, dot. Okay? Guys? There are a couple of ways to approach this problem. One, we can think about writing an explicit formula for this thing. So S of n equals our initial term plus the difference times n minus 1. Okay? The difference here, we have to analyze this first. And once you analyze, you realize there's a difference of 2 each time, right? Okay. Our initial term is 1. 1 plus 2 times n minus 1. That's one method. The other way is you can read the problem statement. It says our odd numbers are twice a number minus 1. Or S of n equals 2n, 2n minus 1. Either way. Either way is fine. Are there any questions about that? Yeah?
What about Sn equals n plus n minus 1?
N plus n minus 1. Well, yeah. N plus n minus 1. How many n's do we have?
Well, I put the n minus 1 in parentheses.
How many n's do we have?
2.
2 n minus 1. Same thing.
Oh.
These are all three the same thing. Angela?
Right, but wouldn't that be 2n minus 1n?
Nope. We're not saying n times this
Plus, okay.
plus. Big distinction. Alright. Any questions on that one? Then let's go to the next one. The next one says, prove that 121 is in fact an odd number. There's a couple of ways to do this. Some common things I saw from you guys. 121, if you divide it by 2, you don't get a whole number, so it's got to be odd. Yeah, that's true. The other way to think about this, though, is you're going to get more complex sequences and series. In 121, they're saying should be a solution to this sequence. What that means is for S of n equal to some terms, 121 should be in there somewhere. If it is in there somewhere, can someone tell me anything about the nth term? It's got to be a whole number. It's got to be a whole number. Okay? So if we take 121, set it equal to our equation, 2n minus 1, what should we do? What should we do? Yeah.
Add 1 and then divide it by 2.
Perfect. We're going to solve for n. Add 1, add 1. We get 122 equals n. 2n. Divide by 2. Divide by 2. We get 61. Okay. Is that a whole number? Yeah. It's a whole number. It's a term in that sequence. It's a term in that sequence. And that's something I want you guys to take away from this. Is that, yeah, odd numbers you can work with, you get the idea, you divide by 2, it should be a whole number. Or it should not be a whole number, in case of odds. But when you get to more complex sequences and series, keep in mind, you go through all this pain of developing these formulas, use them. Try to use them. Any questions on that? Okay, last.
Wait,
and the-
how does that prove that it's an
Think about the domain for n. 1, 2, 3, 4, all the positive integers. The domain for n is every positive integer. Is this a positive integer? Therefore it's an odd number. Let me say that again. N is an element of positive integers. Okay? N's an element of positive integers. Which means, if I take any positive integer, it's going to spit out an odd number.
in that formula?
In that formula. Any positive integer I choose, pick a positive integer. 3. Great. I plug 3 into this formula, I'm going to get 6, 5. I'm going to get 5 as an output. Okay? That's an odd number. I plug 61 into this formula, I'm going to get 121 out. It satisfies this equation. If it came out as a decimal, what Abril was saying, it's not a solution. It's not an answer in this set. So what I can do with this is I can look long term, any number I want. I can go up into billions. Pick a number, 1,543,012. Is that an odd number? Well, no. Okay? And that's an easy one, because we have an understanding of what even and odd is. But if I give you a more complex sequence, like say, the sevens, so 7, 14, 21, 28, 35, so on and so forth, and I go up to say 435, is that a 7? Does that satisfy that sequence? And we can either divide it by 7, or we can plug it in and solve for n, see what we get out. Okay? Other questions?
No.
Okay, the last one. And I'm not going to lie, if you made this mistake, this is a clue you need to come in and get help. You are given O of 17 equals
0.
Okay. Okay, it stood for odds. So
Oh, it did.
it stood for odds. So in any case, when you see this notation written this way, guys, what do we plug the 17 in for? And if you didn't do this, and if it was because you thought this was 0 times 17, fair enough. But if you thought that this was something else, and you did not understand that you need to plug it in for n, you really need to come get help. Is that clear? Alright, we're not going to go on that one. Okay, so, here we go. So let's talk about these 4 sequences. We've got a function. We're saying let f be the quantities 0, 1, 2, 3, 4, and 5 map to 1, 2, 4, 8, 16, 32, such that x maps to 2x. We've got our diagram that shows where they're mapping to. We've talked about this a few months ago, this specific setup. We've got a sequence that represents this equation. Is that a recursive or an explicit sequence? Right?
Explicit?
Nope. Yeah, well, there's one option left. Recursive. Why is it recursive?
Because it's giving you the next one.
You need to know the prior term in order to calculate the next term.
Yeah.
That's recursive. Explicit, we just need to know the first term, we can calculate any term.
Yeah, we don't even need recursive.
Hmm?
We don't even need recursive.
Recursive, to be completely frank, is not that beneficial. We usually want to get the explicit formula. Alright, and then we've got a table. We've got a table. So, the question here was, how are these representations alike and how are they different? How are they alike and how are they different? What do you guys think? Oops, sorry. Yeah, what do you got, Brennicky?
Okay, I said the table of the function and the diagram are alike because they show actual beginning and ending numerals, while 3 just shows the change that is occurring. And also, the function and the sequence show what occurs up to the end function, while 1 and 4 will only show up to a certain limit.
So you're calling 1 the table, 4 the diagram,
Yeah.
and 2 and 3 are function and sequence. Okay, cool. I'm sorry, say that again. I was trying to follow along with your numbers.
The first one or the second one?
Both.
Okay. I'll just say, like,
Okay.
So the table, the function, and the diagram are like because they show actual beginning and ending numerals,
Uh-huh.
while the sequence just shows the change that is occurring,
Okay, so it shows the relationship between the two.
right?
Alright.
The function and the sequence show what occurs up to the end function, while the table and the diagram will only show up to a certain limit.
Okay. I would argue with the function one only because it has the formula in there as well. I'm not sure if the notation,
But
the formula, you were saying something along the lines of, these have, they have a terminus, they end at a certain point. And I thought you grouped the function in there for that. Is that not the case?
no, I said that the function and the sequence shows what occurs up to the end function.
Okay. Okay, so we're going up to that. Alright. So basically these are all different ways of representing the same information. We can have a finite amount of information, which is what Brinicke's essentially hitting on, that we get a couple that go a specific distance. We have a couple others that we can use indefinitely and go on forever and ever and use for any sorts of numbers. The biggest distinction that I hope you guys got out of yesterday was that if we're talking about if we're talking about sequences and series, we're really limiting ourselves to integers within our domain. When we start talking about x's, we're expanding that from integers to all real numbers. Okay? So, like that. So, let's look at our notation really quick and make sure we're all on the same page before we move forward. Basically on this warm-up, there may have been a couple of things that you guys noticed that were slightly different. What we're going to talk about today is really getting into this discussion about domains and ranges. And there's a few notation things that we need to see. So, you're going to see today things like capital X. Since my capital X and my little x look similar, I put the bars on the capital X. And this is kind of the equivalent we talked about of the capital A and the little a back in like September when we first introduced ourselves to sequences and series. The capital X represents the entirety of a sequence. Represents the entirety of the sequence.
What do you mean?
Meaning, capital X represents everything in here. 1, 2, 3, 4, 5, 6.
Oh, and little x is just one number.
Little x just represents one number. Okay? Alright. We're going to see another notation that looks like this. F colon x to y. F colon x to y. So there's a function f that maps x as an element of to y, which is an element.
Was this supposed to be notes?
Yep.
Wait, packet is notes?
Well, I'm providing you some things you're going to need in order. Yes, that's yours. You can write on it. You can write on it. You can put wherever you want. I'm just trying to give you guys some context of what we're about to see. And this is going to be the big one.
So the F1 we should write down?
Yep. So F colon capital X to capital Y. Now let's make sure we understand what this says, because this notation is starting to get a little gross.
Can you read it?
Yep. So F colon capital X to capital Y says there is a function f, some rule. It could be a sequence that we've talked about. It could be a sequence that we're working on converting into an equation that we can use for more general purposes. Think about the exercise we did yesterday where we went from the discrete data where we're talking about specific points for those examples to when we converted it to a function that could represent any real number. Okay? F represents a rule that we're going to define. And it maps all of these little points
Maps X E.
to all of these little points.
So it like compares them?
No, it's a rule.
Well, that's what I meant.
Wait, what is it?
Like
It means
X.
that there's
Okay.
a y for every x.
Yeah,
There's one y,
that's what I'm.
there's one y for every x. So there's some rule that's gonna